let's get started with this class. And for those of who couldn't make it, we're going to record the lecture as usual. So we're going to look today at the P version of the finite element method. And as we said many times, one way to reduce the error is to reduce the size of your elements. That is the p-FEM or the H version of the finite element method. Today we're going to learn to do to reduce the error in a different way, keeping the mesh fixed. And now we're going to reduce the error by increasing the polynomial interpolation order. Okay. So some definitions before we get started officially. So what we're going to look today is only 1D. So we're going to look at 1D p-hierarchical finite element shape functions. And it is very important that you choose the right basis for p-FEM. And for that I actually have, let me just look at the figure. So I'm going to borrow this figure here from the book. Okay. So what you see in this figure is something very interesting. On the left you have just the monomials. So you see psi squared, cube, and so on. And what you see is that as you increase the order of the polynomial or the monomial, right, what happens to those functions? Let's just take the positive side between 0 and 1. What happens to those functions as you are increasing the order of the monomials? Yeah.
They start to deviate more from the linear.
Yeah. They deviate more from the linear, but if you take, for example, the linear and the quadratic, but then you take to the power of 8 and to the power of 9. So what is the difference there? Huh? Of course, they become more steep, but what I'm looking from you is
less variation.
Huh?
Less variation.
Less variation. That is what I was looking for.
Sure.
So that means that if you take a look at the linear and the quadratic, so if you take a look at this and at this, you could say that they are different, quite different, right? But if you take a look at, let's say, the last two, they are not that different. So that means that monomials are actually a really, really bad basis for p-FEM, because as you increase your polynomial interpolation, you're not adding a basis function that can add much better behavior. In fact, this has the consequence of deteriorating your condition number of your final stiffness matrix. So if you take a bad basis for your polynomial interpolation, eventually, as you ramp up the polynomial order, you can obtain a singular stiffness matrix. And that is why we never work with a basis like that, but instead we're going to work with the type of polynomial functions that you see on your right. So what you see on your right, these are called Legendre polynomials. And a nice feature of those, right, is that they are all orthogonal to one another, right? So orthogonal in the sense that if you try to integrate the product of two of those functions, right, in the domain, in this case minus 1 and 1, that integral is going to be 0. So they are orthogonal in that sense, in the sense of the inner product. So as you can see then, as I am increasing the polynomial order, I am introducing new capabilities. So because then I'm able to represent new behavior. You understand intuitively how that works, right? So we're going to start with some definitions. What is the space of functions that we're going to be dealing with? Again, we're going to talk about some space that I call SPH for a fixed mesh size. And I'm going to define this space as some functions U such that U is a member of that energy space that we have seen already, and also that function U belongs to space P pi, so sub pi, that is defined on an element ei, and this is for all x belonging to that element. And of course I have to do the same for all elements in the mesh. So this goes from I equals 1 to the number of elements. So all of, what this is saying simply is that if you just take a finite element like this, we're going to be dealing with functions that are square integrable, so they are belonging to that energy space, and that they are just polynomials. So all that fancy mathematical representation is just to say that the functions that we're going to be dealing with are just polynomial functions. Of course, we have to define what that P space is. So this is the space of polynomials of degree less than or equal to P I. Right? And as we said, we're going to be dealing with the Legendre polynomials. So let's see how they look like. So if you take P equals 1, let's say this is my these are the functions that you already know. So for P equals 1, everything remains the same. And now we take a look at P equals 2. So this is phi1, this is phi2, my phi3 is going to be equal to some function that I am going to define in a minute. And of course, we have to keep that, right? We have to keep the linear part, otherwise the space is not complete, and we always need to include a complete space, right? So that means that if we are going to be dealing with a polynomial interpolation of order 4, so then we have to keep the linear, the quadratic, and the cubic, as well as the quartic components. For q equals 3, then this all remains the same. And then we're going to add yet one more function. That is going to look something like that. And so on. You can keep adding polynomials to this basis. So we talk about the advantages of using this. Orthogonal polynomials are going to give you the best condition number of the stiffness matrix. And they have also a very nice property, is that all these Legendre polynomials can actually be computed from a recursion. Yeah, who knows what recursion means? Okay, yeah. So you can in order to get the polynomial of degree 10, you can reuse all the polynomials up to degree 9 in computing that polynomial of degree 10. And because of that, this can be implemented in a very nice recursive way, right? Using recursion. That means that in the computer implementation, you use a function that calls itself. That is what we mean by recursion. Okay? And who has read the chapter on p-FEM that I posted on the Nota Bene already, or started to look at? Yeah. So you're going to find code there that does exactly that. That you can basically call the function for computing Legendre polynomials recursively to compute a polynomial of degree, I don't know, whatever. It's arbitrary. Okay.
Susan,
Yeah.
question for P2. Do you actually add a new node in the middle of
That's something that we're going to discuss because it's a very, very important question. And we will see what's going to happen. So far, we have been looking at the H version of FEM. And if you remember, we discussed this idea of the H version of FEM having this Kronecker delta property, right? Where basically, if you evaluate a shape function at the location of its node is equal to 1, but at any other node is equal to 0, that Kronecker delta property is going to be lost here, except for the linear components of the polynomial. Because all the polynomials that I'm going to be adding to this basis are going to be 0 at the end nodes. So the linear polynomials are going to keep this Kronecker delta property, but all the other degrees of freedom are not going to have this. All the other shape functions do not have this property. Okay. So we will see later why that is. Yeah, but it's very, very nice because then if you think about the degrees of freedom for p-FEM, you can only say that the displacement at the end nodes represent the displacement at those nodes. But if you want to evaluate the displacement at any point inside the element, right, you are going to have to evaluate the entire expression. Okay? So, in other words, the degrees of freedom that are associated to high order shape functions are not going to physically represent the displacement at that location. Okay? Everybody understood this? Yeah? It's a very important, but we will look at this again. So if you didn't get it, then we're going to talk about it again.
Could you describe what you mean with the first advantage?
Yeah, so what we said earlier is that if you look at the shapes of these polynomials, right, you just look at the shape, they are orthogonal. That means that when you are going higher in polynomial order, you are indeed introducing new behavior. That was contrary to what is happening here, that the higher the polynomial order, those polynomials are actually getting closer to one another, right? So you can think of, say you have a very, very high order p, and then you take p plus 1, those functions are almost exactly the same, right? So you do not introduce new interpolation capability to the approximation, right? So the bad effect of using those monomials then it's going to be that since all those functions are alike, right, for very high orders, then it's like you are introducing rows to your Stiffness matrix that look exactly the same, right? So then you have this linear dependency issue that makes your Stiffness matrix singular. Yeah, and so using Legendre polynomials or any other type of orthogonal polynomials for that matter, like Chebyshev polynomials, is going to give you the best condition for the Stiffness matrix. You have a question there?
Yes.
Yeah.
This reasoning you applied just now, that we check that at zeta is 1, or near zeta is 1. Would you say that at zeta is minus 1, the polynomials are different enough?
It's the same. If you look at this side, let's say negative, right? You see that the shape those functions have, the last two, is very close to one another, right? Yes. So in that regard, it's also deteriorating your condition number as you go up in polynomial order, right? Whereas here, you can clearly see that no functions are alike.
Yeah.
Yeah, and that is what we mean by you can get, by the use of orthogonal polynomials, the best condition number. You have a question there?
Yeah, this implies that only integers are used for the value of p, but could, for example, be a p-value of 3.5 be optimal too?
That is no longer a polynomial, right?
Yeah, okay, so
So we're going to be dealing with just the polynomial spaces. You could, of course, use anything you want, right? And as we already know, you can add something to your approximation, and then Galerkin is going to do its best to minimize the error, right, with whatever we want to give. But the problem with your suggestion is that if you add something that is not a polynomial, then you have to integrate it, right? And to integrate something that is not a polynomial is going to cost you more than integrating polynomials. Why is that? Who can tell me?
Because the rule is straightforward.
Huh?
The rule to integrate a polynomial is straightforward.
Yes. N points integrate exactly what? A polynomial of degree?
N plus 1.
2n minus 1. Yeah, these I'm going to ask you again. Yeah, but this is very important. So polynomials, you can integrate them exactly with a few Gauss points, but the moment you introduce functions that are like rational functions or something else, like an exponential, you can do that, but then you have to deal with integration. And that becomes, sometimes it's actually a matter of research in itself. For those of you who are going to follow my second class on enriched finite elements, who's, come on guys. Well, we are going to do that a lot, because what we want to do there is we want to improve the approximation. And if you know, for example, that you have a singularity because you have a crack, and adding a singular function is going to help you in recovering a better approximation, then this is what we do, right? We add a function that is singular, that behaves like that, and then we actually manage to obtain a better result, an approximation that is much better than just using polynomials. Okay, but again, on the downside, you have to deal with integration issues. So let's move along, because we do have a lot of material to cover today. So we said that since these are hierarchical functions, we say that basically to compute a polynomial order p, then we can reuse everything that we have computed up to p minus 1. So let's just state that. That's one way to say it, so that it is simple. So if we try to go from quadratic to cubic, we can reuse linear and quadratic terms. But as you saw, I have used a function phi hat that I have not defined yet. So let's define that function. So that function phi hat looks like this. And that is what I mean by reuse, right? Give some order and I call it this order here J, right? That goes all the way up to P. You can see that to compute that polynomial, I'm basically using recursion because I can actually call this function in itself. So here I need the Lagrange polynomial, sorry, a Legendre polynomial of order J, and then I can call J minus 1. And basically in the implementation, what you see in the book chapter that I gave you, this function is actually calling itself, which is something very handy, okay? Because the implementation turns out to be super simple, and it's very nice. But why do we do that? Why that expression is like that? Because this way of expressing the orthogonal polynomials has a very nice consequence. In the stiffness matrix, do we use the polynomials themselves? If you think about the stiffness matrix of an element, the integral between -1 and 1 of EA times the derivative of the shake function with respect to x times the derivative of the shake function with respect to x, and then we have the Jacobian and then d psi. We are not using the shake functions themselves. We're using the derivatives, okay? So if I want to have a good condition number in the stiffness matrix, right, I actually don't want to use the Legendre polynomials as they are, because then when I apply the derivative, this orthogonality condition is lost. You guys understand that? Yeah? So what do I want to use? I want to use orthogonal polynomials so that the derivatives of those orthogonal polynomials are actually orthogonal.
You integrate the polynomial.
Sorry?
You integrate the polynomial.
Yeah, so that's why that expression is here on top, is doing the integral. So if you think about what I'm doing here, you can actually show that, you can actually prove that if you do the integral between two functions, yeah, this is actually going to be equal to the Kronecker product, the Kronecker delta, right? This is called Kronecker delta. So the derivatives, the integral over the derivatives, that's why we are expressing that phi hat in this way, so that that integral holds. Yeah? And because in building the stiffness matrix, we're using the derivatives, this is the property that we want to keep. Okay? You could, of course, use the orthogonal polynomials as they are as well, but the condition number is not going to be as good as if you use this form of polynomials.
Sure. Could you
Yeah.
explain, please, what condition number is?
The condition number is a measure that you obtain if you take your stiffness matrix and you compute the eigenvalues of a stiffness matrix, and you take the maximum eigenvalue and you divide by the minimum non-zero eigenvalue. That is your condition number. So when your condition number is infinite, right, that means that your matrix has an eigenvalue that is equal to what? 0. And can we solve that system?
Single.
It is singular, right? So can we solve a singular system? Actually, we can solve a singular system, but you have to do it in a specific way. It's not straightforward. Okay. In fact, sometimes in enriched methods, when we add something that is already represented, let's say you have your finite element, linear or quadratic finite element, and then you add as an enrichment a linear function that already is represented by the partition of unity, then you are introducing this linear dependency, and then your system becomes singular. Can we solve it? Yeah, we can still solve it, but you have to use tricks to get around that singularity. Okay, so that is condition number. Let's move on. So I'm just going to summarize what we discussed. Okay, and because of this Kronecker delta property, so we're integrating in the entire domain minus 1, 1, and that integral is basically the Kronecker delta property, then that results in a really nice condition system. And then once we have all this in place, so now we have a way to build these shape functions. So now everything else remains the same, which is nice because everything that we have learned already for h-FEM applies to p-FEM very nicely. And then this, as we have done before, can be written as a dot product between two vectors, as before. And it's nice because now everything we do is exactly the same as we did before. We just have to stack all these shape functions together in that vector. And our implementation remains the same. Of course, there are some subtleties that we're going to discuss, right? Because now that we are dealing with higher order polynomials, what do we have to do with the number of Gauss points? We have to increase them. And what about the mapping, right? Before in h-FEM, we were using a linear mapping. And now we're dealing with shape functions that have arbitrary polynomial interpolation order. What do we do with the mapping? Remember this idea of isoparametric formulation, that we express our field in the same way we express our geometry. But now the field is represented with a high order polynomial, a complete polynomial. What about the geometry? Do we need to represent that in the same way? No, we don't. In fact, it would be silly, particularly in 1D, to use a polynomial of degree 10 to map a line element in master coordinates to a line element in physical space. Yeah? So we're going to keep our geometric mapping linear, which is very nice, right? And then the formulation is going to be isoparametric.
Subparametric.
Huh?
Subparametric.
Subparametric. That is a word. So now our formulation for p-FEM is going to be subparametric because the geometry is interpolated with a polynomial of degree lower than that of a field. So what if the geometry was approximated with a higher polynomial than the field? How would that be called? Superparametric. Yeah. Do you have superparametric formulations out there? Who has a guess? Yes, you do. You do have. And for example, all this stuff that people are doing with isogeometric analysis, or like those are formulations where the geometry is represented exactly, right? So if you can represent your geometry in an exact manner, and if your field is linear or quadratic, then that is superparametric. But those formulations have issues. I'm not talking about isogeometric analysis, but formulations where your field is linear or quadratic and then your geometry is exact have issues in the way you represent rigid body modes. So lots of information. Yeah. So let's continue because we do have a lot of stuff. So as we said, we're going to use the same linear mapping as before. But then this is going to lead a subparametric instead of isoparametric. Okay? So what is our mapping? Well, our mapping, if you remember, we were using just the hat functions, 1 minus psi That's it. And then the x is equal to the length of the element divided by 2, and this is what we defined as our Jacobian. And keep in mind that this j, it is not the same j that I'm using here. Okay. All right. I have to figure out a nice notation to be consistent throughout. Normally the capital J is referred to the matrix of the Jacobian. So yeah, it's a bit tricky. The thing is that J and is also used for indexes normally. So anyways, let's look at an example how this would work. Now we're going to look at a very simple problem. 3 elements. And what I want here is to use p equals 1, p equals 2, p equals 3. This is my first element, second element, third element. So if we try to plot the functions, of course I'm going to have my nodes like that. And we're going to have our hat shake functions. In the second element, I'm going to have a quadratic function, also in the third element. And then I'm going to have some cubic function at the end. So let's label them. phi1, phi2, phi3. I am missing one function here. phi4, phi5, 6, 7. So again, you know that okay, so that is how we're going to solve this problem. If you notice, it's very simple to mix polynomial interpolations at any portion of the bar. And who can tell me why that is? Why it's so straightforward to have one element with p equals 1 and let's say the contiguous element with p equals 10? Who can tell me?
Should not put the order of the first element also to 10, but its pre-factors all 0.
Sorry?
Well, you could also consider the first element as a polynomial factor for the 10.
Yeah.
And then give all the shape functions a pre-factor of 0, so that they don't compete.
Yeah, you could do that. But what I mean here is that in our interpolation, we have chosen the first element to be p equals 1. And let's say the contiguous element could have p equals whatever you want. And it's very, very simple to mix different polynomial interpolations in contiguous elements. Why that is?
It's because only linear terms are non-zero at the nodes where the elements.
That is correct. All the higher order polynomials, starting from quadratic and above, all those polynomials go to 0 at the nodes. So if I have one element with p equals 1 and the contiguous element is p equals 10, right? This is still a conforming discretization because all the high order polynomials go to 0 at that node that is shared. And this nice property also extrapolates to 2D. So in 2D, you can have a very complicated mesh, and you can say, well, I want this quadrilateral element to have p equals 8, and the neighboring elements p equals 2, for example. Yeah? And you still have discretization that is conforming. Okay? Who knows what conforming means? So much information today, guys. Have you heard about the term conforming or non-conforming? No? So in finite element analysis, a conforming discretization means that all nodes, right, are shared by elements. The moment you have a node, right, in an edge that is not shared by that edge of the element, it's called a hanging node, and that basically leads to a displacement field that is discontinuous, and that is called a non-conforming discretization. Okay? So in p-FEM, you can see that creating a non-conforming discretization is actually not possible because this property that all the polynomials vanish at the edges of the element. Okay? All right, so let's represent that field. So we have phi1. And I'm just going to summarize. Yeah. And of course, you can say that you can represent that like this, as we said earlier. And another way that I like to write that discretization is I want to say that, well, if I say if I write it this way, I like it to write it in this way because here IH is the index set of nodes of the mesh. So the first term is actually the linear part of your approximation. And this second term is basically containing every other nonlinear term. Yeah, and I actually like to write it this way because you can think of p-FEM as a way to improve on your approximation by adding nonlinear functions to the whole formulation. So this for me is already an enrichment over your linear interpolation. You can think of it as, adding something to an approximation that is going to help you reduce the error, and that is what we do in enriched finite element methods.
What does the backslash mean?
Yeah, it's a minus, subset minus. So here I'm saying I belongs to the set of nodes that is basically all the nodes minus those that are the standard nodes. Yeah. So let's write that again. So if you take a look at UH evaluated at x2, right? We say that this phi2 of x2 times u2, and we know that because of the Kronecker delta property between the linear shake functions, this is equal to 1, right? And every other shake function is equal to 0, so I have only that term. And then this is equal to u2. And so the degree of freedom, u2, has the same meaning as the displacement as before in h-FEM. Yeah, and now let's take another point. Say we take and we evaluate the expression at a location that is in between node 3 and node 4. Something like that. Well, we know that the linear shape functions are going to be non-zero, so we're going to have, let's call this guy here x prime. So we're going to have phi3 evaluated at x prime plus phi4 evaluated at x prime u4 plus phi6 at x prime u6 plus phi7 at x prime u7. Yeah. Keep in mind what is our point here. Let me just let's plot it in this blue. So we're looking at this point here. Yeah. So because it is in the middle, we know what is the value of this, the linear interpolance. What is this value?
0.
Huh?
0.
No.
1.
Yes, it's 1/2. And we know what this is, which is 1/2. And we know what this is, 0. You're on fire today. So this one is 0, and then you can see that this whole thing leaves us u6, which is what we discussed earlier, right? That u6 has no longer the physical meaning that is attributed to those in h-FEM. Yeah, in fact, what you can say is that, well, if I apply the derivative, the second derivative in this case, of UH, this is going to be equal to U6 times the second derivative of phi6 evaluated at x prime. So you can say that U6 is more related to the derivatives of the field. Like those degrees of freedom are more related to higher order derivatives. Okay. Okay. Yeah.
Sure. Could you explain again why U6 has no longer a physical meaning?
Yeah, because this is your displacement evaluated at that location. Yeah. If U6 had the meaning of the displacement at that location, that means that this should be 0, this should be 0, and this should be 0. Well, the last one is 0, because the shape function at that location is 0, but the first two are no longer 0. So in order to get the displacement at that location, you have to evaluate the whole expression, which is what we said earlier in the discussion, right? So what I'm trying to say is that if you look at h-FEM, we all know that the degree of freedom at a node immediately is associated to the displacement of that node, right? That property in p-FEM is lost and is kept only where? At the end nodes. So at the nodes of the element, even in 2D or in 3D, this still holds. But only at those locations, right? This property holds, right? In h-FEM, if you remember, we look at, or in the project, you have a Lagrange element that has 3 nodes, so the quadratic Lagrange element, right? You have one node at the end, another node at the other end, and then there is a node at the middle. Can I say that the degree of freedom associated to that middle node is the displacement of that node? Yes. Because of the Kronecker delta property. So if I evaluate the shape function of that node here, right, that is equal to 1, and that shape function goes to 0 here and here. Now, the end shape functions, which are quadratic, are actually vanishing at that location. So for Lagrange elements, we still have, right, this property, the Kronecker delta property, so we can still recover in that middle node the displacement by just looking at the degree of freedom, right? When we go to more advanced approximations like this one, p-FEM, we have to evaluate the whole expression as we are doing it here to obtain what would be the displacement at that location. And you will see this in your project, because when you extend the program in order to plot the displacement field inside the element, you are going to see that you actually need to sample along a few points to be able to see the whole displacement field. Okay, but let's finish very quickly here with something else. Because now we have all the ingredients that we need. We actually know how to build these bases where we're using orthogonal polynomials. And these are a special type of orthogonal polynomials where their derivatives are actually orthogonal polynomials to improve the condition number. And we have everything we need to compute the stiffness matrix, right? So let's take the stiffness matrix. For a 1D bar. Our KE, remember that this is a matrix, but I'm going to just compute the IJ component of that. So if you remember, if we take our bilinear form applied to that element, it was something that looks like this. Yeah, but we never do that, do we? Do we actually integrate in physical space? We replace that integral because we're actually working with a master element d of x. So I have to change that d phi d psi dx, and then we have and then I have to add the Jacobian and let's remember that these two is 2 divided by LE and this one is LE divided by 2. Okay, so now when we are actually going to do numerical quadrature, we replace that integral by the evaluation of that integrand at some fixed number of points that we know that are called integration or Gauss points, right? So we have 2 divided by LE, and then we have a sum I equals to 1 number of Gauss points, and then of course we have to evaluate this whole thing. So this is evaluated at psi I, and then we have the weight. That is not the weight function again, is the weight associated to that Gauss point. Okay, so of course is Wi. And again, how many Gauss points we need? N Gauss points. Two n minus 1. So you see that everything remains the same, and in the implementation, all we have to do is to just stack in that vector of shape functions, not only the linear components, but also quadratic, cubic, quartic, quintic, and so on. And then the operations remain the same. The only thing that changed, as we saw, is that we have to keep the linear mapping of the geometry. And the other thing that changes, right, is that we need to increase the number of Gauss points to integrate that polynomial exactly. Right? And this may not be so straightforward because, well, when we are dealing with a polynomial interpolation of order p, keep in mind that now in the integrand of that stiffness matrix, we have p minus 1 multiplied by p minus 1. So you have to find a nice way to determine automatically what is the number of points that you need. But this basically finishes the p-FEM in 1D. It's very straightforward. So we are going to do p-FEM in higher dimensions, but I want to postpone that for later, because before that, I would like to look at convergence rates. We're going to look at how to divide problems depending on their smoothness, right? Because this is what you need to solve your project. So let's stop here. It took 52 minutes.